So hi, my name is Marcel, and this is joint work with my colleagues from TU Wien, Daneshwar, Amro Ali, Ezio Batocci, George Kennison, Laura Kovac, and Miroslav Stankovic. So solving invariant generation for unsolvable loops. There might be a few terms in here that not everyone's familiar with, but don't worry, we're going on a journey. So we are in the landscape of program verification and analysis. And whenever we want to verify or analyze a program, specifically if it contains loops, we need to find invariants, but there are obstacles, right? So there is, for example, undecidability, which hinders us from finding invariants. However, there are also some tools I'm going to show you today, such as recurrences, that we can use to actually then find invariants. And we're going to use this tool and first go through some easy level solvable loops. I'm going to explain what that is. And then finally arrive at the contribution of our paper, which is an invariant synthesis procedure for so-called unsolvable loops. All right, let's start with a simple example. So this small program here multiplies two inputs x and y. So you can see this by looking at the program variable set that is initialized to 0. And in every loop iteration, we add the input x to set. And the loop is executed a total number of y times. So at the end, the variable set contains the result x times y. So this is an intuitive description, right? But what if we want to prove this formally? What if we have a precondition and a postcondition? We've seen this today already.
It's me. Do you have a microphone?
Makes it fun, right? Yeah. As soon as you start speaking about preconditions,
Something valid.
let's go down.
You need to put this on.
I need to put this on?
Yeah, because there are
Is
some
that good?
people on.
I think this is enough.
Okay.
Just stand here. All right, so I gave an intuitive description, but what if you want to prove this formally? We have a precondition and a postcondition, and we want to prove that for every state satisfying the precondition, we end up in a state satisfying the postcondition. Because this small program here contains a loop, what we need is an invariant that captures the semantics or the behavior of this loop. This expression here, this polynomial equality, is an invariant because it holds on entry of the loop and it holds after every loop iteration. And therefore, it holds also after the loop is exited. And also we know that after the loop terminates, the loop guard is not true anymore. So we have I is equal to 0. And when you substitute 0 for I in this invariant, you get immediately the postcondition. So invariants are important. They are, roughly speaking, properties holding throughout the loop's execution. And I hope I have convinced you. I guess I don't need to convince you. They are important or useful and even necessary for verifying program correctness. They can also be used for loop summarization or code optimization and many more things. However, loops are also the main source of undecidability in verification. In Floyd-Hall logic, if you don't have any loops, the steps can mostly be automated, but if you allow a single loop in a program, your program model is already Turing complete. So finding all invariants is going to be undecidable. But now let's ask the question, okay, this is undecidable in general, but can we compute all invariants for simple enough programs? How simple do we have to make the program such that this problem is solvable, that we can find them? So let's start with level 1, linear assignments. So we only have a single loop, and in the loop body there are linear assignments. Coincidentally, our running example is such an example. So can we find all invariants for this program? And the problem is still not specified enough. So the question is, what invariants? Invariants are just properties about program variables. But what properties are we talking about here? So the invariant we have already seen is a polynomial equality. So let's specify the problem of finding all polynomial invariants. So all polynomials of program variables that are 0 throughout the loop execution. And in the remainder of the talk, I'm just going to abbreviate this equals 0. And whenever you see a polynomial, just think it's like equal to 0. Okay, so can we find all polynomial invariants for this loop here? So we have seen, this is our invariant that we have already seen. But if this invariant, so this polynomial is equal to 0, then so is its square, right? And so is our invariant times anything else. And so is even more complicated combinations. So there are infinitely many invariants. So if you want to compute all of them, we cannot list all of them in a finite amount of time. So what do we do? So yes, there are infinitely many polynomials, but if we take the set of all polynomial invariants, they have a very nice structure. And for those of you interested, or many of you may know it, this structure is called a polynomial ideal. So the name is not that important. It's important that we have this nice structure. And David Hilbert told us already over 100 years ago that this structure has a finite basis. So even though it contains infinitely many elements, it has a finite basis. And Bruno Buchberger, a computer scientist, gave us an algorithm to compute this finite basis for a polynomial ideal. So can we use this machinery to now compute finally all invariants for this program? And we need like one more tool for this, recurrences. So recurrences are a way how to describe sequences of numbers, like the Fibonacci numbers that start with 0, 1, 1, 2, 3, 5, and so on. They follow a very famous recurrence. You start with 0 and 1, and then the next term in the sequence is just the addition of the previous two terms. And recurrences are a very natural way to model arithmetic variables in a loop, because the value of, for example, set in the next iteration only depends on variables, on the values of the variables in the current iteration. And so we can write down recurrences for our program variables to model the values that they are going to take throughout the execution. And in this case, we can literally just read them off, the recurrences, from the loop body. So we have set is initialized to 0, the initial value, and set in the next iteration is set in the current iteration plus the constant x. We can do the same for I. And now we can compute so-called closed forms for these recurrences. So these are expressions that immediately give us the nth term, the nth value of a program variable. So without computing the first values of the program variables. And most importantly, for such recurrences that are linear recurrences with constant coefficients, these closed forms always exist, and we can always automatically compute them. And these closed forms are exactly the thing that we need as an input for this machinery of Gröbner basis and computing this finite basis of the polynomial ideal, the invariant ideal. And if we just consider this as a black box now, but if we feed these closed forms to this black box, we actually get the result that our invariant that we have already seen is actually a finite basis for all invariants of these loops, for all polynomial invariants. So it captures all invariants. So level 1, linear assignment solved. But can we apply the same techniques of recurrence, closed forms, and then Gröbner basis to more complicated programs? So we had linear assignments. So let's just make it a bit more complicated and throw in one quadratic assignment. And we have a new program variable, a, and we have a quadratic assignment. A is assigned a plus z squared. And in this specific example, we can do a little trick. We can introduce yet another program variable, z2, that models z squared, the value of z squared. And it does so by just a linear assignment, right? So we introduce this new variable z2, and in the loop body, the assignment for z2 is just the square of the assignment of z. So you just take z plus x, square it, and then you replace all the z squares in the program by the new variable z2. And remember, x is just a constant, so x squared is also a constant. So the assignments are now linear. We have linear assignments. We are back to the linear case, to the easy case. We can do this whole procedure of constructing the recurrences, solving the closed forms, and using these closed forms then to compute the invariants. Okay, there's a nice trick, but yeah, if you're interested, this is the basis actually. So now we have two elements in our basis, the closed forms. So this is a nice trick, but can we do this now all the time? Does this always work? Unfortunately not. So, but why did it work in this case? And it worked in this case because we have two blocks of variables. So we can partition the variables into two blocks, this yellow block and the purple block. And we have the property or the, we have the facts that within a block there are only linear dependencies among the variables, and all polynomial nonlinear dependencies are only to previous blocks. And such loops are called solvable loops. They were first studied by Rodríguez-Carbonell and Kapur in 2007, and also by de Oliveira and others. And for such loops, this trick works, and we can compute all polynomial invariants. Okay, solvable loops work. But what happens if we move to unsolvable loops? So what can we do there? So in general, this is going to be hard. And here's a very simple loop, like one variable, one assignment, and the assignment is only quadratic. So we didn't make a far jump. So pick your favorite number R, plug it in, and you have a loop. Can we compute closed forms for X? And the answer is no, because this loop, this very simple loop, models a very famous sequence, which is called the logistic map, studied in different areas in mathematics, and it is well known to not have closed forms for most values of R, so not even analytically closed forms. Previously, we had these nice closed forms that were polynomials or even polynomial functions in N, and now this sequence doesn't even have an analytical closed form. But now, there's still something we can do. So here are, again, two unsolvable loops now. So the left loop is unsolvable. We have this yellow block and this red block, and within the yellow block, there is this y squared. So we have a nonlinear assignment within the block. Similar on the right. For the right program, we have only one block and nonlinear dependencies within the block. And you also cannot partition it in a way such that you can make it solvable. These are really unsolvable loops. But you can see the reason for unsolvability in the left program is that we have this y squared in X and this minus y squared in the assignment of 1. So if those were not present, we would again be back to solvable. So in this case, we can actually just see that when we add X and Y together, so X plus Y actually does satisfy a linear recurrence, and it has a closed form solution, although the individual variables do not. And similarly for the right side, you can check that y squared minus x cubed satisfy a linear recurrence. So it's basically the reason for unsolvability, quote unquote, cancels out. So yeah, these are two examples, but can we use this observation to create an invariant synthesis procedure for unsolvable loops? And yes, we can. This is the contribution of our paper, and it follows quite the observation that we made for this example. So the game plan is as follows. First step is that we separate the variable responsible, quote unquote, for unsolvability from the other ones. So in this case, X and Y were the ones responsible for unsolvability, and Z was not involved at all. So X and Y are called defective, and Z is called effective. Right? And the effective variables, Z in this case, they follow linear recurrences. They have a closed form. But the defective variables in general do not. So what we do is we just keep the effective variables. They're not a problem. And similarly to this combination X plus Y, we want to find polynomials of defective variables that are effective, that follow a linear recurrence, that have closed forms. And then we combine all these closed forms together, like the closed forms for the effective variables and the closed forms for the combinations of defective variables, to use it in a downstream task like invariant generation using Gröbner basis, as we did in the previous examples. So the most mysterious step is probably step 3. So how do we do this? So we want to find a polynomial of defective variables that satisfy a linear recurrence. So we first fix a degree up to which we want to find such a polynomial. Like for the sake of this example, because we had like x plus y behaved nicely, let's just fix degree to be 1. And now the problem is to find coefficients a and b such that ax plus by is effective. And now we look at what we have. So what we can do is we can construct a recurrence for our combination ax plus by. Right? This recurrence, we can construct a recurrence for every individual variable, so it's not a problem to construct a recurrence for the combination of them. This recurrence might not be linear, it might not be solvable, but we can write it down, we can get it. And then we have a look at what we would like. So I said that we want this combination to follow a linear recurrence, to have a closed form. So if you do the math on this, what you want is that our combination ax plus by in the next iteration is a multiple of itself in the current iteration, plus some other inhomogeneous part that is effective, that we can handle. So this is like not a problem. And now we have these two things. We have the thing that we have, the recurrence for our combination, that is dependent on the coefficients. And we have the thing that we want, that it follows a linear recurrence, also dependent on the coefficients. And what we can do now is we just equate to 1 and 2 and solve for the coefficients. So, and if you do the math on this, it turns out that this leads to a quadratic system of equations over the coefficients. And this means we can find all solutions for these coefficients. So theoretically, you can find all solutions, and also practically by using a computer algebra system. And for this example, if you follow this procedure, you get set the effective variable that was as before, you get a closed form solution, but also you will recover what we just saw with our own eyes at the beginning, that x plus y is a combination of defective variables that behaves nicely. And then you can use these closed forms again with standard invariant generation procedures to convert this into a basis for your invariants. And what is I would say, nice thing about our method is that we can find all of these nice polynomials of defective variables up to a degree d. And so for solvable loops, we could find all invariants with unbounded degree, and for unsolvable loops, as we have discussed in this one example, it's going to be hard in general. We're going to lose something. So what we lose is, so we gain, of course, invariance, but what we lose is that we have to fix the degree of the defective variables up to which we want to find invariance. And we have implemented our invariant synthesis procedure in our tool Polar, which is a loop analyzer. It's also specifically a probabilistic loop analyzer. So if you have probabilistic choices within a loop, and our invariant synthesis procedure also generalizes to probabilistic loops, then you have invariance over moments or expected values. I'm not going to talk about that today. If you're interested more on the tool Polar itself and the theory behind it, there's also a talk on UPSLA that I will give on Friday. But we have implemented the synthesis procedure in Polar, and what you can do is you have an unsolvable loop, like with nonlinear dependencies, and you just give the source code to Polar. You will have to specify here, it's probably small, the degree up to which you find nice combinations of defective variables. It takes the program, in this case, tells us that there are actually 6 classes of combinations of defective variables here, x and y, that follow a linear recurrence that behave nicely. So to conclude, invariants are central for program analysis and verification, and finding all invariants is undecidable in general. For linear loops and also for solvable loops, we can use techniques such as Gröbner basis computation, Buchberger's algorithm, to find all invariants. And then the contributions I showed you from our paper is we gave a characterization of unsolvable loops in terms of these effective and defective variables. I described it quite intuitively here. If you have a look at the paper, it's a bit more worked out and theoretical. And then this gave rise to this synthesis algorithm for well-behaved or quote-unquote nice polynomials of defective variables you can use for invariant synthesis. Then we have in the paper also applications for deterministic and probabilistic loops, such as also dynamical systems and things like that. Thank you very much.
Thank you for the very nice talk.
So I have two small questions. The first one is on the previous slide. You showed the program outputting these Grosvenor bases, and I guess the last one was the most obviously nice one, as in it had the fewest terms. I don't know if it was this slide or yeah, I guess.
Yeah.
So are all of these equally good for having an invariant, and is it just that you could decide some simplicity criterion to select the simplest invariant and then use that one?
I mean, the invariant you want always depends on what your post condition is that you want to prove, for instance, or yeah, what you want to do with the invariant, basically. I wouldn't say necessarily that the last one is the best one, because all of the 6, I can't pause it because it's a GIF. This just gives you the complete information. So these are all the combinations that there are and all the closed forms that there are of combinations of X and Y. And if you want to now move to concrete invariants, it depends on what you want to do with this invariant. If I presented at the beginning that the goal is to compute all invariants, all polynomial invariants, then you would need to consider all of these closed forms together. Right? You use all of them in this procedure.
Mm-hmm. So it's not true that you could conclude one from the other using just an SMT solver?
In this case?
Yes.
No, in this case, they should be distinct, right? There are some parameters here. You see, like on the bottom, there's U6. So this is going to be a solution for any real number U6. Yeah, they should be disjoint. They're independent in the algebraic linear algebra sense.
Mm-hmm. Yeah. Okay, and I had another small question. You showed inference over, I guess, algebraic expressions. Did you consider at all, say, some kind of abstract function and a recurrence using a function which is not an algebraic expression?
So if you have, you mean in the loop body, if you have more complicated structures there?
For example, if in the loop body I repeatedly apply function f.
Yeah. So no, we didn't try this. The whole thing is based on algebraic geometry or recurrence relations. You need a ring for that, and then you could do the things that you want to do. In the paper, you will see we also abstracted a bit away from the concrete loop, because the thing is that you have the recurrences, right? That you can imagine that there are in between the recurrences and the actual loop, you have some abstraction already. So you have the loop and you abstract the behavior of the loop body, although it contains many different constructs. You over-approximate it, for example, by linear recurrences. So you lose some information. But then get back to the recurrences. But we didn't try functions, repeated function applications.
So thanks for the nice talk here. I'm not sure I understand exactly what is the gap. So from your problem statement at the start is you want to find all invariants that can be written as a polynomial, as polynomials or the finite basis.
Yeah.
And then you said that one issue is that you have to fix the degree, and then you find a polynomial that takes these defective variables and turn them into effective variables. Is there always a degree that exists such that you can transform these defective variables into a polynomial, and that gives you an effective variable? And also you had several times like this nice, within quotes, nice polynomials. Maybe I missed this, but what does that mean?
Yeah, so with nice, well-behaved, I always meant that the combination follows a linear recurrence with constant coefficients. So it has a closed form solution. That is what I meant with nice and well-behaved. It's quite long to say follows a linear recurrence. What was the first question?
Is
degree D.
Yeah, so if basically there exists a finite basis that gives you all the polynomial invariants, does there exist a degree D such that basically we can use your method to find this basis?
Up to degree D. So there might be also know combinations of defective variables that satisfy a linear recurrence. So then there is no degree. You can search up to where you want. That's also the problem, because you can increase the degree and increase it more and more, and you don't get a combination, then you don't know it. There's like one future work we are thinking of. If there is a criteria that we can increase the degree and then at one point stop, and have a criteria to say that we don't have to look further. But here you move very quickly into algebraic geometry and very high algebraic geometry. But we have a mathematician on our team, so it should be fine.
Thanks. And quick minor question, maybe. What if you have conditionals in the loop body? Can you do something?
Yeah, that's a very good question. Yes, short answer is yes. I'm going to talk about conditionals in the Uppsala talk on Friday. So if you have a probabilistic loop here, you can have conditionals under some conditions. The question is, can you construct the linear recurrences out of it? And you have to have some restrictions on the if conditions such that this is possible.
Thank you.
I was just going to ask the same question about conditionals. You know, I recall reading papers about finding loop invariants way back in the 80s, where they talked about solving these recurrence relations and so on. But people recognized very quickly that a major stumbling block was dealing with conditionals. So I'm surprised you didn't address it at all. And I'm inclined to say, if you're not dealing with conditionals, can you deal with real programs? So the kinds of things you're showing there don't occur in a lot of programs that I see.
Yes, so
real programs have conditionals.
Yeah, I mean, as I said, the question is, can you go from the program to the recurrences, right? And for the probabilistic loops, I'm going to present on Friday, we have a method to go from conditionals. You need some restrictions on the conditionals, but you can do it. I would disagree with that. These are the only programs that you can see. Like we have one case study in the paper. Dynamical systems can always model by such loops, and they often have nonlinear behavior. So one case study is, for example, a biological system of like grows, how bee population grows. There are no conditionals in there, but very high nonlinear behavior, and you can find an invariance that say something about this biological system.
Sure.
Yeah.
Okay, so thank you, I'm here. Thank you for your talk, from presenting this really cool technique. And over there, this way. But so I was wondering a little bit about if you had some motivation for why you chose to focus on polynomial invariants, and if you have any idea of how it would be possible to extend to other kind of invariants.
What can I ask? What kind of invariants are you thinking of? Inequalities?
Yeah, if you have inequalities, if you have max operations, if you have some conditionals. I don't know, like stuff that are made up of other things than polynomials.
Yeah. So polynomial invariants, we started it because there was this gap of solvable loops, and we wanted to push that forward. And there is this nice structure that you can exploit whenever you have other invariants. When you want to tackle other invariants, the question is what structure do you want to exploit? And we have focused on that basically for that reason, because of the structure.
Hi, thank you very much for the very clear talk. So I wanted to ask, I guess that for unsolvable loops, the approach will take longer if the degree increases, if D increases. And so I was curious to know whether you know what is the algorithmic complexity of your approach with respect to D, or maybe you haven't looked at it. But...
Yeah, great question. So the thing is, we have to find these coefficients, and the higher you make the degree, the more monomials you get. Basically, we only have a linear function. You get more and more monomials, and for every monomial, you have a coefficient. So this is going to very quickly become very expensive. That is true. But the main complexity is not in finding these combinations, but then in the end solving the recurrences. It's much more expensive, and so this step doesn't hurt, so to speak, to do it before.
Okay.
If this answers your question.
Yep, thank you.
So this is cool. Thanks for the talk. I'm curious if you've thought about how this procedure could be refined or modified if you knew what property you were trying to prove when you were producing your invariants.
So when you have a pre and post condition already, and you wanna, for example,
Yeah.
find the right invariant.
Yeah, seems like maybe you could. So there's a situation where you just can't produce invariants that help you prove a property, right? The property you want to do, which is a possibility. But there's also a possibility you're going to produce a bunch of invariants that are unnecessary for proving a property. And I'm wondering if you could use a property that you are targeting to restrict that search in some way, or if you've considered how you might do that.
Yeah. I can't think of a way on the top of my head, but I'm sure there must be something, because there are a lot of ways you can basically tweak the process when you the slides are gone, but when we construct this candidate where we have to find the coefficients, I'm pretty sure there would be a way, like you can definitely restrict the search space of these coefficients, and maybe you could inform basically the search space of the coefficients.
But I'm also wondering if you could,
Yeah.
choose a D more intelligently.
Yes,
if you know
or
what you're
a
trying to do.
degree. Yes, yeah, that would probably be the first step. Yeah, to choose a degree. Yeah, because in the very first example, I think at the very beginning, at this one on the right side, we had this. It was a quadratic invariant, and I'm pretty sure that you could say probably that you don't need 1 of the 10th degree or something like that.
Thanks.
You were saying you're looking for stuff that has a closed form. What is a closed form for you?
Excellent question. So the most important thing is that we have a linear recurrence with constant coefficients, right? Because those can be solved automatically. I don't really care that much about the closed form, but I can solve the recurrence. And it so happens that linear recurrence with constant coefficients, these ones, they always have a closed form that is comprised of polynomials and exponentials. So you have like polynomial functions in n. Basically, n is the number of group theories. You can have polynomials times 2 to the power n plus polynomial times 3 to the power n. That's what I mean.
Cool.
Okay, we can thank the speaker again.